But yeah, so let's get started. I know Pernika can't make it. I actually haven't heard from Lydia. I know she wasn't at the last one, so maybe I'll connect with her afterwards. But let's get going, and then if other people join, then I have to kind of have a hard stop at 5. So
yeah, let's get started.
Works for me.
Cool. All right. So I think last time we left off here, right, at the classification. Right?
Mm-hmm. I think we left. Yeah, I think so.
Okay, cool. So I thought I would go through the rest of it and then do the exercises. And there's a bunch of different kinds of exercises from this chapter. Some of them are kind of those like how to load data and plot things in the lab part. And then there's these conceptual questions. I was thinking of just going through the conceptual questions.
Yeah, that sounds good.
Okay, and yeah, we could talk about other stuff too if we have time. All right, so I'm gonna go down here. Feel free, as always, to interrupt me. And in terms of scheduling, I know Pernika, she will be here next week, and she's gonna do chapter 3. So that's really, she was able to sign up for that.
Perfect.
And I wasn't originally going to be here next weekend, but I probably will be. Yeah, so I was going to be on vacation, but it's kind of, our plans are in flux, so probably we'll be here. Anyway, so let's get going in this part. Let me know if there's background noise or something, or you can't hear me well enough. I can try to change that, but yeah, just let me know. Is it okay right now?
It's okay. Sometimes I hear like ping pong balls, but yeah, it's fine. No, don't worry about it.
One of Finn is playing indoor golf, so
got it.
These ping pong like balls, so
it's not bothering me at all.
Okay, cool.
Yeah.
Cool. All right, so classification. So we talked about kind of regression, a lot of regression scenarios, and classification is when we have kind of a categorical outcome, either like a binary outcome or something that's not able to be ordered. All right, okay, 1 second, sorry. All right, and we're back. Other one needed to show. All right, sorry about that. So basically, in these classification settings, so either we have a binary outcome, like 1 or 0, or we have kind of different categories. These are often like like some kind of a factor or a set of categories that aren't ordered in any way. They're just they're you're trying to predict basically what class something belongs to based on the observations, based on the predictors. They talk about here as a simple in kind of in general classification settings, error rate here. So basically what this is they're saying, if whether or not the predicted value is equal to your observed actual outcome. And if it is, give it a 1. If not, give it a 0, and then add them all up and average and divide by the number of observations. So that'll give you just the fraction of incorrect classifications. In this case, they're talking about it as a training error because we're computing it against data that we're using to train on. This is not like what is happening right now is particular to any sort of one classifier. We're just talking about classification in general. And then kind of the same thing for the test set, right? So you're giving predictions. If the class does not equal the observed class, then give it a 0. If not, give it a 1, and then average all those up. So here, I guess they're just doing shorthand for this formula. Kind of similar as you would write in code. Okay, so yeah, and they're just using the same subscripts here to refer to the observation number.
Sorry, Kevin, what is I?
Yeah, so I is just the observation number. So like, let's say you're predicting.
Oh, okay.
You have 1,000 rows, and this is you're talking about your test set. You don't know what the before when you're doing predictions, you don't know what those outcomes are. But anyway, the 0th row, the first row, second row, all the way up to.
Oh, no, I meant that large capital I.
Oh, sorry. Yeah. So Ronald may know this for sure, but I think what it's saying is like, it's like, I think it's like a first identity, but I'm not totally sure.
Okay.
I think it's like this is going to be like a Boolean.
Yeah, it stands for indicator.
False or indicator. Okay.
Indicate. Okay.
Got it. Yep. See, I knew someone else would know. Yeah. So I think it's like, if it's false, if it doesn't equal each other, then it's a 0. If it's true, they do equal each other, then it's so on.
Okay.
So then if you were to add up all of those and divide by the number of observations, then you get a kind of an error rate of how often you're wrong.
Okay.
How often you're right. Yeah. Yep. Thank you for that.
Yes, thank you.
All right. So then they talk about this kind of generalized idea of a Bayes classifier. This was actually confusing to me at first because this was not clear to me in the chapter when I read it through it, that it's like kind of like a hypothetical, like perfect knowledge scenario. Because they talk here about later here about the error rate. And I was like, how is the error rate going to be like? They're basically saying the error rate is like the like for each observation, you have a probability that it's going to be one class and probability that it's going to be another class. And if you choose the maximum of those two, like if it's a 70% chance it's going to be one class and a 30% chance it's going to be other. If you choose the maximum, then you're going to choose that class that has a higher probability, but 30% of the time you'll be wrong. And what was confusing about it to me was like, they're just taking that and saying that 1 minus that is the error rate. And I was like, this is just a model. Like, how could you just take the error rate from this?
Right.
But it's assuming that like what those probabilities are, like like it's a kind of a hypothetical model.
Yeah.
So that was confusing to me at first when I read through this. I don't know about you guys, but I was like how can you just take the error rate
I agree.
Probabilities you're estimating? Yeah. Sorry, go ahead. Yeah.
I just saying I agree. It was confusing for me too, not just you.
Okay. Yeah. And then I read through like to the end, and I think after the section I kind of got there, but yeah, it was confusing up front. Okay, so basically anyway, so they're saying that a Bayes classifier is just you have a certain set of predictors for an observation, predictor values, and based on those values, you're saying you're giving probabilities to the outcome, the different classes. So it's just 2 cases in my output, based on these values of the predictors, you have 60% chance of being cat and 40% chance of being a dog. And maybe based on, in the second row, it might be 90-10 or 99-1 or 50-50, et cetera. But just the basic general idea is that you're based on conditional on the values of X and for that particular observation, that's going to produce some kind of probability distribution or probability of the outcome being a certain class. Okay. So, and then they're showing this 2-dimensional predictor space where you have 2 kind of different predictors, X1 and X2, 2 different variables. And the colors represent different classes. Basically, if you have, this is kind of like a hypothetical model here that produces a decision boundary. So what the decision boundary would do is say everything to one side of the boundary is going to be one class. So in just this case, like blue, whatever blue represents. So let's call it something real, like an apple or a blueberry. And then in the other case, it's going to be an orange. And so it draws this boundary, and then basically based on where these observations fall on these 2 dimensions relative to this boundary, it'll say, okay, everything over here is a blueberry, everything over here is an orange. And so you draw it all along here, and it kind of learns that whatever this decision boundary rule is based on the algorithm for the classifier and kind of the values that are observed, so x1 and x2. And so you kind of look through here and see, and the colors represent kind of like the true known classes. So if you were to draw this, so in general, this classifier would get most of these predictions correct, these classifications correct. But there are a few that, kind of buck the trend a little bit, that appear on the other side of the boundary and that are a lot closer to, mostly if you look in the neighborhood of these values, most of them are like oranges, but this is a blueberry, right? But in general, it would be a pretty good boundary. Okay, and then here's where I was confused in the book, right? They say that the Bayes classifier gives the lowest possible error rate. So, oh, I see. So the lowest possible test error rate. Yeah, I didn't think about that actually, because I didn't read this as with the lowest possible first. To think a little bit through that language. But
I think the point is that there's a fundamental stochastic nature to this model, in that the guys near the boundary can be a blueberry or an orange if they're close to the boundary. Right. And there's nothing you can do about that. It's irreducible, right?
Right, the irreducible noise that we talked about. Yeah, that makes sense. Right. Yeah, so I guess like it's also the lowest possible error, because with that stochasticity, if you have you're getting the maximum of the predicted probability as your class, and in the most optimistic scenario with this kind of known set of probabilities, 70% of the time you're going to be right. Let's say if it's 70-30, 30% you're going to be wrong for that individual prediction. But in other cases, it could be worse than that, depending on like how big your sample size is potentially, or just due to kind of the random nature of this data generating process.
Yeah, I had to really think hard about this the first time I saw that equation. My eyes kind of glazed over. I'm like, huh? So I just thought like an example, like your blueberry orange thing. I didn't think of blueberries and oranges, but there's only two categories, so J just ranges over two things. And so if you're near the boundary, if you're actually on the boundary, right, then it's 50-50, and the irreducible error at that point is going to be 50%, right? There's nothing you can do about that.
Yep. Right.
That kind of helped me when I thought of it that way.
Yeah, that is really helpful. The Bayes error rate is analogous to the irreducible error. Yeah, and like there's no pattern to that at all, right? It's like as good as white noise, basically.
Yeah, that's how I was thinking of it.
At that level, yeah, there's no structure to it, and like when you have a more like where you have a case where there's a class that has a much higher predicted probability than the others, then there's much more structure you can learn from that, because 80% of the time it's going to take on one value based on these predictor values, and 10% of the time like there's, I guess, like as the probability for one class goes up, there's less irreducible error. Is that a good way to think about it? Like if one class is predicted at, if this Bayesian like probability estimate is like much higher for one class, like 80, 90, 95%, then the error rate's going to go down, but like there's less of that irreducible error component.
Yeah, I think that's right. You're averaging over all the data points, so it's really, it looks like the data points near the boundary are going to dominate that error rate. So the ones that are all far away, where it's like 99%, they're not.
Right. So depending on like Yeah, right. Yeah. Interesting. And
yeah, I still haven't. Tell you the truth, I still have some trouble figuring out how it works with actual I guess maybe we'll get to some actual in practice of that. Hopefully, it'll make more sense. Because
yeah, that's helpful. And then I think here E is expectation, right? So it's like the average. Okay.
Over all the data.
Overall the data. Yeah.
Oh, it says over all possible values back. So maybe it's not just the data; it's just like an integral, I guess. I don't know.
So like the entire population, if you were to theoretically have it for this setting.
Yeah, is it all the X data points, or is it all X? That's what I can't figure. Like integral, even hypothetical data points that you didn't have.
Yeah, they say all possible values. So I think
that's possible makes you think it's an integral, right?
Maybe. Yeah. All right. Let's go on to this right here.
Hopefully it'll become clear when we get some actual applications. I hope.
Yeah, and I think this chapter, like, I try not to worry too much about some of the details of these, because they're giving you, like, chapter 1 was a very high level about the book. Chapter 2 is kind of like your first pass at a lot of this stuff, and then I think there'll be individual chapters on each of these concepts. So, or and more, obviously, but yeah. So try not to fret too much about that. But,
right.
Okay. So key nearest neighbors
is overall observations.
I think you're right.
Possible.
I think I was reading more. Yeah, I agree with you. I think I was reading more. They said, for our data, the error rate is 0.3133. So that means that, they didn't do an integral. They must have just summed up over all the data.
Right.
Cool. Okay. So they talk about key nearest neighbors, which is one way to kind of one approach to do classification. Let's see here. So approaches. Okay. All right. So basically, in this case, K represents an integer. So when you're running this classification algorithm, you're choosing a value for K up front. So you're saying, K of 3 or 4 or 5, 100, etc. And that's for every single observation, it's going to use the K number of closest points to that observation, kind of look at the class of those nearest points, and basically the majority class of its neighbors it'll use to make a prediction for that point in question, is like the basic idea. So here you have a point in question, or I think so, right? X, I think X here represents that point that you're trying to classify. You have 2 blueberries and 1 orange in that radius here, in this 3-point radius. So you'll predict that X will be a blueberry. And here they're just showing that there's like multiple decision boundaries here, or multiple kind of decision points based on the application of this algorithm. I think it's, again, K equals 3. So if you look at anyone,
same with me. I love your example of the blueberries and oranges.
Cool. I was like, they're not giving a real variable here, so I just called something, but I don't know. Cool. I'm glad it's like helpful. All right, so let's say we're talking about this point here, right? The 3 closest points are 1, 2, and 3. They're all blueberries, right? So we'll call this blueberry. And here, again, we have 1, 2, 3. 2 out of 3 are blueberries, so we'll call it a blueberry. Here, I guess it's probably 1, 2, 3. So 2 out of 3 are oranges, so we'll call that an orange, etc. So they talk about, like, basically it's a relatively simple approach in terms of being able to talk through it, but you can get decision boundaries and classifiers that are actually really close to that optimal, kind of best error rate classifier. And they're showing here different boundaries to different K choices of K. So here we have K equals 10, and kind of it produces this, you know, kind of somewhat jagged decision boundary, where everything on this side is going to be considered blueberry, everything on this side is going to be considered an orange, and they're showing this is the actual decision. This is the decision boundary for this K equals 10. Black is kind of that optimal Bayes decision boundary, and it's relatively close. And then if you choose different Ks, it's that boundary is going to look a little different. So with K equals 100, so as you get higher, it seems that this decision boundary gets a little less kind of nuanced, because you're looking at this huge swath of points, you know, around every point that you're trying to classify. Sorry, I'm just reading through this again. Oh, sorry, I got the flipped up here. So the black curve is the K nearest neighbor decision boundary. The dotted one is the optimal. So yeah, so here, right, you get kind of a less nuanced, less jagged boundary, because you have to consider, you can't like provide a local estimate for this class at this value. It's considering kind of like half the data set every time. So it's going to be much straighter and much less kind of jagged as you go up in your K, the number of points you're considering. Does that fit what everyone else was thinking here?
Yeah,
that makes sense.
Yeah. So with K equals 1, you know, if we're thinking about that from last time, kind of the idea of model flexibility, it's going to be very flexible. It's going to be able to learn some of these really kind of minute or kind of irregularities, or like nonlinear, if that's the right word, kind of boundary patterns. As you go up, it's going to be less flexible. Okay. Nearest neighbor methods can be lousy when P, the number of predictors, is large. Okay. Interesting. Reason is the curse of dimensionality. Nearest neighbors tend to be far away and high dimensions. So I guess, yeah, that makes sense. So if you have a ton of dimensions, it's less likely that you'll find points that are truly like similar to each other in all those dimensions or many of those dimensions. Just like it's harder and harder to find similarity between observations when there are more and more dimensions to consider.
A question, Kevin. You can table it if you know it's kind of off topic, but I'm just wondering. So I don't know if I think maybe in the exercise it goes over how they compute the distances for this K nearest neighbors, right? But is it similar to like a clustering approach, right? Where you would be computing, I don't know, either correlations or some distance measure, right? To determine if the points fall in separate groups.
Mm-hmm. Yeah.
Because I'm thinking, right, if you had something like this, these oranges and blueberries, like you're saying, right?
Yeah.
Could you first use a method like clustering to see maybe if they separate by some other measure, right? And then that would maybe allow you to, I mean, I don't know. That's why I was thinking based on the math, if it's similar. Like, would you know?
Mm-hmm. Yeah. I guess my thoughts are, I think distances are kind of considered in similar ways.
Right.
So I think the example or the exercise, they're talking about Euclidean distance. So kind of looking at the difference on every predictor and squaring it, adding them up and taking the square root or whatever. And I think in a lot of clustering approaches, you can apply a similar distance formula to like figure out, to measure kind of how far the centroids at the center of those groups are. So I think that there's a similarity there, and like, and obviously in the choice of K, I don't know like
Right.
It's a good question. So like, I guess in this case, you know how many groups there should be, right? So you know that
Yes.
there should be, so like in the clustering approach, K is the number of groups. And in this case, right? Or no, K nearest neighbors, never mind. I was totally wrong about that. Yeah, I don't know. Like you would know how many classes there are, right? And
Well, for clustering, sometimes yes, and sometimes you don't know.
sorry, I mean in this
Right.
case where it's like blueberries and oranges, and you were to apply K nearest neighbors
Yeah,
clustering
right.
to it.
Right. Yeah. You're
That's
right.
what sorry, that's what I meant.
No, my bad.
I don't know. I'm just kind of like fumbling around here. I don't know, Ron, do you have any thoughts on that?
I've never actually done clustering before, so I don't know much
Okay.
about it at all. I'm hoping to learn about it, but
Yeah.
I'm actually
Okay, yeah,
paging
no,
the book saying,
I've
do they
done-
cover this later? I don't know.
No, sorry. I was just thinking, because I've done some clustering like hierarchical, but
Mhm.
so there's many measures of distance that you can use for specific things. And so I was just wondering, how this relates to this K nearest neighbors. But yeah, don't worry about it, Kevin. Your thought process helped me think through it too.
Yeah.
So once we get into maybe either clustering or actually doing like this KNN,
Yeah.
that was my question. So
Yeah, I
Thank
guess
you.
it's like, yeah, it's from my initial thoughts, like it's similar in terms of you're going to choose, and for this, you could also choose another distance formula. With
right.
with clustering, you're trying to figure out both how many groups there are and which points belong to which groups, right?
Right.
And like where those boundaries are. So it's also kind of drawing some boundaries. Yeah, but I guess you're using, in the clustering approach, you're using the distance and kind of the density of points around the middle of a group as like the way to determine which observations fall in which group. Yeah, I have to think through it more. I'm like not able to articulate much more about that.
No,
but,
that
all right,
actually makes sense. Yeah.
Anyway, okay. All right. So let's go to here. Okay. So tuning. So this actually looks a lot like the curves that you saw in the previous section, where they were talking about in general, if you have more and more flexibility, you're getting kind of improved train and test performance at first, and then you have kind of this U shape where with more flexibility, it starts to hurt you in terms of variance, right? Like you're chasing irreducible error, kind of sample to sample, and overfitting here, but then you can kind of reduce this training error with that flexibility, but it's going to really hurt you in a test scenario. And so the level of flexibility here is 1 over K, which I think makes sense, right? Because in this case, we said that a lower K is going to be more flexible and a higher K is going to be less flexible. So all the way over here, right, you have, it would be 1 over 100, which would be this case here. And then as you go to the right, K is getting smaller, right? Yeah. Which represents a case like this on the other extreme of 1 over 1. Yeah. All right. Anything else here? So yeah, I think that just the general point is that we have this characteristic, this U shape here. All right. So that's actually it for this section. We'll go there's definitely more on unsupervised stuff later. Here, like down, where is it? Unsupervised learning. So I believe there'll be more here. K-means clustering. Look at that right here. All right. So we'll get there, and yeah.
At the very end. Yeah.
Yeah. All the way in September. We'll be there.
Yeah. When we're all old friends by then.
Yeah, exactly. All right, shall we jump into the exercises here?
Yeah.
I have some notes I wrote on my own. I didn't make any modifications yet. I wanted to see what we all thought in each of these before we. Oh yeah, blueberries and I didn't even see the chat. Okay, that's awesome. All right. So in this first part, so like I said, I haven't made any modifications. After the discussion, I'll maybe change some things or make some suggestions for additions. But yeah, I wanted to answer it together before we do that. So for this, they're just saying in the first part, we would want to indicate whether or not the performance of a flexible or statistical learning method would be better or worse than an inflexible method, and justify your answer. So in this first case, we have a large sample size and the number of predictors is small. So the answer that other cohorts provided here is a flexible model can take advantage of a large number of observations to make a detailed model. And yeah, that makes sense, right? Like if you have a small sample size with a flexible model, it's not going to be making many assumptions about what that underlying functional form is, or there's more kind of tunability of it. And you might that kind of more sophisticated pattern is going to be harder to capture if you have less observations. But the more observations you get, the more it can learn kind of if it's a complex pattern, you're going to want more data to be able to get closer to the true reduced bias, get closer to that true a true functional form. So I feel like that's just like a kind of, straight from their discussion of like bias and flexibility. Anything else on that? I feel like I like that answer.
Yeah, that makes sense.
Anything else anyone wants to add?
No.
Okay.
So
right.
My question.
Yeah, go ahead.
So does that mean like deep learning model where they are saying they need large data? So is this be congruent with what they are saying? Like since deep learning is flexible model, that is why we need large data, right?
Yeah, absolutely. I think that's 100% correct. Yeah. So the more kind of you get these models like deep learning models where you have a ton of parameters to estimate, the more data you're going to need to properly estimate those parameters.
Right.
Yeah. So what is the essence of this? The number of predictors is small. What about if we see the number of predictors is large? What does the effect of the number of predictors here
in this question,
given the size of the data set?
Yeah, that's a good question. Yeah, anyone have any thoughts on that? I might have to think for a second about that. Yeah,
I'm not entirely sure, but wouldn't you always, and I also don't know, but that the large sample size with a small number of predictors almost sounds like an ideal situation, right? For just about any model, because then you could really infer what the relationships between those predictors are on your outcome. So if you have too many predictors, is it normally the case that you want to reduce them somehow for whichever model you're using, right? Because otherwise it gets complicated.
I think that's basically correct. But I think what you'd want here, the problem is you have a large, even though you have a large sample size, my thought is if you have a large number of predictors, you probably have some like spurious correlations between those predictors and everything. You're going to have to like sort that out. So you're going to want a less in my view, you'd want a less flexible model for that, at least at first. Maybe even just look at linear just to see what's going on and see what's correlated with what, right? Because all those predictors are relevant. So reducing them, I think you're right. That's like your first goal at that point. I think. I don't know.
I think you're right, and I think it also depends on the model as well. Because some models are going to really struggle with high dimensionality, and you want to like collapse that somehow. And some are able to kind of derive those features in the model training process. It's like automatically basically. And in those cases, yeah, like you might not need as much to do that. Or like with, you know, a regression context, you have issues with like multicollinearity or whatever, where you have problems with I think the standard errors of the coefficients if you have too many terms that are correlated with each other. So like I think there are certain cases where if you're using that kind of model, you definitely need to use, like as the next question that says PCA or something to get it to get that reduced. But yeah, they're talking about ordinary least squares.
Oh yeah, that's kind of this.
Yeah, exactly. But I also think, which is another point about, like, if you're talking about like a deep learning model or something that's incredibly flexible, I think actually if you have more predictors, like if you have 1,000 predictors, it's just going to make your sample size requirements even larger, I would think.
Right.
Because it's just going to up that complexity, up that space that you're trying to understand, right? Like if you're, you know, in that 2-dimensional space, you're trying to figure out for a classification exercise that a line, right? But then for 3-dimensional case, you're trying to estimate this like plane, and et cetera. So like, yeah, so that function that you're kind of estimating is, you know, I would think that with more predictors, you want way more kind of, I don't know what the right scaling relationship is there, but you definitely need more N when you have more predictors, I would say, especially for a flexible model. Yeah. Okay.
That makes sense.
So, second case, the number of predictors is extremely large, the number of observations is small. So yeah, so I think definitely I agree with this answer here. You would want an inflexible model here, right? You want to make more assumptions up front about the functional form, but also probably use something like PCA to, depending on what kind of model you're using, to reduce dimensionality, because there are definitely issues when you have way more observation, or way more, you know, you have a wider than data set than longer than it is long. You're going to have issues with kind of variance and things like that. You know, if you don't do things like PCA in that case, but I would say definitely an inflexible model would perform better in many of those cases, because you just don't have much to learn from, and you need to make more stringent assumptions about the underlying functional form to have any sort of good performance in that case.
Oh, that's a great way of putting that. I like that.
Yeah, cool. And I think if you're using a super flexible model, you're really in danger of overfitting with less data. You know, like a smaller data set is going to have more, I would say, more noise, like, or more relative. You know, you're going to have a more variance and relative to the variance in like the population. And if you have a super flexible method, it's going to chase that variance, but it's not going to, or chase that kind of irreducible error component, and you're going to get some form that doesn't really represent, isn't close at all to the true underlying form. Okay, cool. Anything else on that? All right, C. So the relationship between the, oh, sorry, go ahead. You're gonna say something? Okay.
Oh no, I just said no, nothing else for me. Sorry.
Okay, no worries. C. So the relationship between the predictors and response is highly nonlinear. So I guess I agree that most things being even, a flexible model could better capture the nonlinearity. But like, you could have a very inflexible nonlinear model, right? Like, it doesn't necessarily mean, flexibility doesn't necessarily imply anything about the functional form itself. It's just saying something about how it can adapt to the input, right? So like, if you know that this process is very nonlinear and you use your domain knowledge and you choose a nonlinear functional form, maybe like something like a I don't know, like, some kind of like polynomial or regression or something like that, then it's not incredibly flexible in the sense of like a deep learning model. But you're kind of using that knowledge to restrict the form itself. And I feel like, to me, I feel like it depends on what your comparison is in this case. What do you mean by flexible and inflexible models in this case? I don't know what you all think like about that. But
I agree. I don't think it's necessarily clear. You could go ahead. Sorry. Go ahead.
No, go ahead.
I was going to say I agree with you, because you're right. Sometimes like, oh, this looks very nonlinear, but wait, if I take the logarithm, now it looks, linear, and I expect it to be logarithm because it's a growth model or something, right? So I agree.
Right.
Domain model could mean it's not clear from this C is automatically flexible or inflexible.
Yeah. So
It depends.
Yeah. So what I would say, like here, they said nonlinear. So we know in less flexible model, we make assumption that the relationship is somehow linear or nonlinear. I think the answer is they said a flexible model could do better. We know flexible model, for example, neural networks, they are universal functions and they can approximate any function. So in that case, this answer I think is quite good, in the sense that that kind of category neural networks, they are universal functions. They don't need to any assumption, right? And they can approximate any function. So I don't know if that makes sense.
yeah, I mean, I think like the answer, I have no problems with the answer. Like, I think it might be the best answer if you had to choose one answer. But, and I agree with what you said, Shim, but I also think though, like there are such things as inflexible nonlinear models, and like it kind of kind of blurs the lines here, I guess. And I think it makes it a little bit more, a little bit less straightforward to choose just one answer here. But if I were to choose one answer, I would probably go with what they have.
Karen, what would you, can you give me an example of an inflexible nonlinear?
Yeah, I mean, like let's say I don't know, like you had some kind of a like I was saying a second ago, like a polynomial regression, right? Where you
Got it,
you
like
know
a very
exactly,
high degree polynomial.
yeah, where you know exactly
okay.
that your data generating process is that kind of fifth degree polynomial, right? But like it's not going to be as flexible as like a deep learning model, right? But like they don't say anything about the sample size here. Like if the sample size was small and I had that domain knowledge, 100 times out of 100, I'm going to want that fifth degree polynomial, right?
Yeah,
over
I see.
a more flexible model that might need more data. But I guess they're saying like, probably given that you have enough data for either choice, what would you choose? And yeah, I mean, I don't know, maybe we're spending too much time thinking about it, but
I think the terms are also vague, right? I guess it depends also what they mean by highly, like how much is highly nonlinear.
Yeah, right. Okay, well, sorry, Shane, what were you saying?
Yeah, I think she made a point, like highly nonlinear. I don't know what the meaning is highly nonlinear. Like when they say highly, it doesn't mean that really nonlinear. That's somehow. Yeah, I want to ask something also here. When they say flexible model, I think in some other texts, people say complex model. Does that mean it's synonymous flexible and complex model? So when they say complex model, those that can fit very well, like nonlinear, like quadratic, and all those, they sometimes call them complex. So I don't know if the name is still the same with flexible, or they have different kind of nomenclature.
I think flexible just means a large number of parameters or degrees of freedom, right?
Yeah, exactly. I was just going to say exactly that. Yeah, degrees of freedom and the number of parameters you can tune. That you can learn the values of those parameters from data and tune them. Yeah, but the complexity versus flexibility question, yeah, I mean, I would think that it also would correlate. Like the more degrees of freedom you have, the more complex of the model it is.
I think in the next section where we're asked to draw curves, they actually equate flexibility and model complexity. But that's on the answer. So I don't know, if the textbook is also.
Right. Okay. Well, all right, cool.
So maybe interchangeable.
Yeah, that makes sense. Okay, let's go to this one. So the variance to error terms is extremely high. So yeah, I agree with this, that inflexible would be better here. And I think like this speaks directly to the overfitting question as well. Like if there's more irreducible error, like the variance of the error is higher, there's more irreducible error as a proportion of like the total variance of the outcome you're looking at, then a very inflexible approach isn't going to really get that much thrown off that much by that variance, because it doesn't really shift its estimates or parameter estimates very much sample to sample, even though the variance is really high, because there just isn't much it can do, right? But with a more flexible model, you have more parameters to estimate. It's going to chase that variance, and it's going to produce very different curves, very different rules, or whatever you have, whatever you're using, based on the data. And yeah, an inflexible parametric approach would kind of guard against that in some ways. I feel like that's kind of straightforward. Anything else on that? Want to make sure we have time. I know we're kind of running up on. I propose that we skip the example section and just go on to the curve. I think this is useful. We can go back to the examples if we have time, but I don't think we will. All right, so bias variance. So they talk about sketching typical bias, variance, training error, test error, and Bayes irreducible error curve. So we have this irreducible error. I'll start there. That's this black line here. At first I was like, is this a trick question? Like, it's irreducible. So like, it's always it's constant, right? Like it's no matter what model you choose, you can't reduce it, right? Like, unless you, like in some, they talk about irreducible error. Part of the way they talk about it in the book is like, it could be because of the inputs you have, right? Like they're just like features that you don't have that could potentially help you, but you don't have them, so you can't reduce that part of the error. But there's also just random noise that you'll never get at. So that makes sense to me. And then we have bias. So I believe it's the blue, yeah. So basically, as you get more, so the x-axis here, it's not labeled, but it's flexibility. As you get more flexible for a lot of these models, you get a huge gain up front, and then you have kind of diminishing returns. And yeah, and you can kind of reduce bias pretty low if you get a ton of flexibility, especially with a lot of data. Brown is variance. So this is kind of the trade-off that we always talk about, right? That as you get more kind of flexibility and you're reducing the bias, at some point your variance is just going to explode because you're chasing noise, and the flexibility is no longer helping you reduce bias. It's actually hurting you in terms of increasing variance sample to sample, and also problems with overfitting. And then the yellow and green are train and test set mean squared error. So we know that the error is just a sum of this bias, variance, and irreducible error. So as you in the train set, you can just learn as much as you possibly can about that data and overfit it and keep on reducing error kind of forever. But then on the test set, this here, you have this U-shaped curve because you're going to start to suffer from the variance kind of sample to sample on your training set, and start to really get hurt by the variance component of your error over here as you get too flexible. So there's kind of this sweet spot here where you're minimizing error, a kind of a middle ground of flexibility in many cases. Not true every time, but kind of in general. Any other points here on that?
I have a question, Kevin.
Yeah, go
Can you
ahead.
scroll back up to the, okay. So I understand why the bias, right, and the whatever training MSC go below the irreducible error. Why does the variance start below the irreducible error?
So I think I know they had those plots in the book that I think for irreducible error, they're kind of on the same scale as bias and as the mean squared error and the mean squared error for the train and test, these yellow and green curves, like those are all like error rates, right? But these are, I guess, like, think about it, like they're components of that error rate. So these are like kind of overall error rates, and these are components. So like bias is one component, variance is another. So I mean, I would think that like if you were to follow this exactly, right, it should be every error rate should be like should be your bias plus your variance plus your irreducible error. I'm just talking. I don't know if I'm answering your question, but I'm just talking through my thoughts on it.
No, I think that makes sense. But what I was thinking is, okay, so the variance is essentially how well your model would do if you trained it on different training sets, right? And so, or not how well, but how well it would, or how much it would vary between different training sets.
Yeah.
Using the same model, right? So I guess maybe it starts below the irreducible error. Like, I'm just trying to sort of get a gut feeling for it as to why that would go below that, because maybe, so okay, I think that what they said was the simplest or least flexible model that you could fit to data would just be a horizontal line, right? Which doesn't necessarily explain anything in a data set that would be, you know, very complex or
It's
whatnot.
like a mean.
But then, right, so that would be like a floor type of effect. So if you're fitting, say like a whatever, just a horizontal line to every single training set, then it's not going to vary between training sets, but it's also not going to explain a whole lot.
Yeah.
Okay. But still, why is it under the irreducible error?
Remember, the variance is defined by how much the function would change if you change the training set. Like a straight line is probably not going to change very much, right? It's just going to sit there at the
Correct,
error.
Yeah.
So that would be 0 at that point, I think. Like that's what I think is going on there.
Oh, okay. But does it have anything to do with the irreducible error at that point, or?
So I think
so the irreducible error is still there.
Yeah.
I think maybe one way to think about it is like in the very inflexible models, right? If you just look at like these three curves, like the blue, which is the bias, the variance is brown, and the irreducible error, like up here, the majority of your error is going to come from bias, right? Because you're going to be super far away from the true functional form in a lot of cases because it's a very inflexible model, right? So like,
correct.
It's going to be this one plus this kind of on the y-axis plus the y value here, right? So like very little of your error is going to come from variance because there's no flexibility to, and then as you get all the way over here, the majority of your error is coming from variance. So the same amount of that error, kind of the absolute amount, is going to come from your irreducible error, and very little of that error is going to come from bias.
Right. So that's how you would get this green curve.
And then you would add those three up, and you should get that green curve over, or
I
if
guess,
it were over here.
I'm just sort of confused as to why on the left the variance is beneath this, like the irreducible error. Like how are you getting so close to it? And never mind. Yeah, maybe I'm just.
No, I mean, I had trouble with this too. So the way I was thinking about it, I think I mentioned this last week too, is you think about like if you had the real generating process, right, or a simulated generating process, what you do to calculate the variance is you just fit the same thing over and over again for more simulated data and see how much that curve changes, right? So, right, for the same parameters, of course, right? So whatever the real parameters are. So if you fit a straight line to some simulated data, right? It would be like a line with a slope of like, I don't know, 3, let's say, right? Then you generate some more data, you get a line with a slope of 3.1. And the slope doesn't change that much, so that variance is really small. But now if you fit a high order polynomial, you're going to get all kinds of, every time you generate data, you get some kind of new crazy curve. It's going to be very different every single time. There's going to be a high variance. And that's what the variance is, like how those curves are different from each other, I guess, from fitting
Right.
different data sets. So it would be 0, I guess, if you had no parameters, because in that case, you just always get the mean over and over again. How much is that going to change? Well, I guess it wouldn't be 0, it'd be very close to 0, because it's going to be whatever the standard error of the mean is, right? So it'd just be the mean over and over and over again. It's not 0, but the difference between those different curves is very close to 0, because it's the standard error of the mean, not what the actual mean is, which is that black line. At that point, if you're just fitting a 0.
Is this just the mean? The horizontal line?
It's the mean error, right? Or it's mean squared error.
I thought it was the irreducible error. So
yeah,
I thought that was just a noise term.
You're right. But I explained that very badly.
No worries.
Suppose the mean is 0, right? For whatever this thing is. I'm just going to fit a 0 parameter model, which just calculate the mean, right? So what's the error on that going to be? It's going to be the standard error of the mean, right? So it's going to be pretty small. It's going to be less than whatever the variance is. The variance is going to be, well, square root of n bigger than that, right? Or standard deviation is going to be, of the actual data is going to be square root of n bigger than that. So that's how it can be smaller, I guess. That explanation also was not very good, but hopefully put some seeds in your brain to think about later.
Yeah. I think that's a good direction, though. Is like
I apologize. I have things in my head that aren't coming up very well.
We should just put the formula for these 3 things up here, and then I think you have to like reason with the syntax of like how you're calculating each one, and then in what case one could be bigger than the other, and I don't know, like. Maybe that's the way to do it. Okay.
Yeah. I don't want to take away from our time on other questions.
This is like exactly
very fruitful. Yeah, very fruitful discussions.
Okay, I know we're past 5 here. Hold on one second. I just want to look at what my notes. I had like some things I wanted to specifically cover. So I guess we could stop, but I said I wouldn't be here next week, but I probably will be. I won't be on vacation because the household COVID situation.
No.
But so Parnika is going to present it, chapter 3.
Cool.
But I feel like, I don't know, should we discuss any questions we have about the remaining exercises in the chat? And then because like she's not here and I could talk to her, but I also like, this is a very long book and I don't want to continually push back like the next piece of it, you know?
Yeah.
So I think what I propose we do is if we have any other discussion points we want to have, we can put it in our channel. And then because like there's a few of these I was you know, I slightly disagree with some of the answers and I just wanted to talk about them, but I guess there aren't that many more aside from the examples. What is it? There was one that I just wanted to say something about, and then we can end.
Okay, cool.
All right, so 1 second. Maybe I don't see it though. I'm not finding it. Okay, whatever. I think we have other discussion points on this. We should bring it to the chat and just like put it in there. We can start a thread. And then Parnika will go ahead and do chapter 3, the first kind of the concepts on Sunday next week. Does that sound okay?
Yeah,
yes.
That sounds good. I also figure like, you know, because chapter 2 is still, you know, introducing to all these terms, we'll probably learn this as we actually do the actual modeling in future chapters. So
yeah,
it
sure.
won't be forgotten. Yeah,
I agree with her.
I think you're right. Yeah, I guess one of the like I was like, I think on one of the questions where it was like, how many predictors are there in this case? They said 4 in one case, and like
it was 3, right?
And well, I don't. Oh, I'm not sure. Like what I was gonna say, there's one where I thought it was instead of 4, and I thought it was 5 because like they also said
Oh,
there was a week. They were like the week of this, sale or whatever it was, and I was like, you can
Yeah.
use time as a predictor. Anyway, that was one of the things. But anyway, yeah. If there's anything
Okay.
else, let's do in the chat, and then we'll have chapter 3 next week. I also think it'll be exciting to get into stuff where exercises are. So I don't see any exercises here, but the exercises are, modeling, right? And we're like actually estimating things, and I think that'll be fun to get into that kind of thing.
Yeah.
So cool. All right. Thank you so much. This was fun.
yeah, thank you so much, Kevin, and everyone for their input. I feel like, it was a great discussion.
Agree.
Okay, thank you all.
Yeah, I
Thank
agree
you,
too.
Thank you. See you next.
Thanks. All right. Well, I hope you all have a good rest of your Sunday, whatever time it is where you are, and
Excellent.
we'll talk to you later.
Alrighty.
Okay.
Good Sunday. Bye.
All right.
Bye.
Thank you.